we have our function f of x equals x squared. Now, we had a little bit of trouble thinking about a possible inverse for it for the following reason. F of minus 2 equals 4, and that's this point right here, but f of plus 2 also equals 4. But then, if there's an f inverse, what would f inverse of 4 be? F inverse of 4 is supposed to be the number x such that f of x equals 4, but here we have two such numbers. That's a big problem. Graphically, we see that the problem is that this horizontal line intersects the graph in more than one point. And remember that if f has an inverse, the graph of the inverse would be the reflection across this line. Well, this is what we get as the reflection of the parabola, and the horizontal line is now a vertical line. So this reflected graph fails the vertical line test. It's not a function. So we get what we can call a horizontal line test for determining whether a function has an inverse. If a horizontal line intersects the graph of a function in more than one place, then the function will not have a complete inverse. One way around this is to split up the function. If we look at just the right half of the parabola, that does satisfy the horizontal line test. And that corresponds to this half of the reflection. That's the positive square root. Whereas the left half of the original graph corresponds to the negative square root. But the positive and the negative square roots, those are just partial inverses, because they only work for part of the original function. We'll talk more about partial inverses in the next video. For now, let's discuss functions that don't have this problem of two different inputs giving the same output. We'll start with a definition. We say that a function f is 1-to-1 if, whenever you have two different inputs, so a not equal to b, then you get two different outputs. In other words, f of a is not equal to f of b. So if your function is 1-to-1, it will have a complete inverse function. And if it's not, we'll have to be very careful. How can we tell if a function is 1-to-1? One way is with algebra. Given an output value y, you could solve the equation f of x equals y for x, and just show algebraically that there's only one solution. That'll be one of the exercises. But a lot of times it's easier to use calculus. For instance, take g of x equals 2x cubed plus 3x minus 1. This is a cubic, so its graph might look like this, and that's not 1-to-1. But some cubics look like this, and that is 1-to-1. How would we tell which one this is? Well, I don't want to set 2x cubed plus 3x minus 1 equal to y and solve for x. That's just really ugly. But let's look at g prime. G prime of x equals 6x squared plus 3. And note that this is always positive. So that means that g is always increasing. So its graph is definitely going to satisfy the horizontal line test. And that means that g is 1-to-1. And 1-to-1 functions are those that have inverses. We have some problems to help you chew on this, and when you're done with those, we'll talk about what we can do with functions that aren't 1-to-1.